Okay, everyone, we are going to get started with the next session. And it is my great pleasure to introduce one of my all-time favorite people, Kate Crawford. She is going to be our next invited speaker. Kate has spent over a decade studying the social impacts of large-scale data, machine learning, and artificial intelligence. She's a distinguished research professor at NYU, a principal researcher at Microsoft, and a visiting researcher in the MIT Media Lab. In 2016, she co-chaired the Obama White House Symposium on the social and economic implications of AI. I attended it. It was epic. And as well as publishing in a whole bunch of amazing top-tier academic journals, Kate's also written for the New York Times, for Harper's Magazine, and the Washington Post. As if that wasn't enough, she's also advised policymakers in the White House, the Federal Trade Commission, the United Nations, the European Union, and the City of New York. She's a badass. She's also the co-founder of the newly formed AI Now Institute at NYU, which is the first research institute of its kind that works across computer science, social sciences, and the law to better understand and address the social implications of machine learning and AI. So with that, please join me in welcoming Kate.
Wow, that was such a generous introduction. Thank you, Hannah. I think you are the original badass, so I can but step in your footsteps. Hi, everybody. This is a truly epic room. I kind of feel like I need like a smoke machine and a really big electric guitar to sort of justify this space, but I think we'll just have to press on regardless. So it is an honor to be here, and I want to say a particular thank you to the organizing committee for inviting me to be part of NIPS 2017. My name is Kate Crawford, and I've been studying the social implications of large-scale data, machine learning, and AI. And I think we're at an extraordinary moment right now. We're basically at an inflection point where the power and the reach of machine learning is rapidly expanding into many areas of everyday life, from healthcare to education to criminal justice. Just have a look around this room right now. Machine learning is huge. The old school crew have just been telling me that this conference used to have 200 people. You are now more than 8,000 people strong. So something very big is happening here. And I tend to think of the rise of machine learning as being every bit as far-reaching as the rise of computing itself or of mass media in the 20th century. A vast new ecosystem of techniques and infrastructures are emerging, and we're just learning their full capabilities. But amongst the very real excitement about what we can do, there are also some really concerning problems arising. And as this community knows better than anybody, forms of bias, stereotyping, and unfair determinations are being found everywhere, from machine vision systems and object recognition to natural language processing and word embedding. And you probably saw the many high-profile news stories this year about bias, from women being less likely to be shown high-paying jobs to gender bias in object classification datasets like MS COCO, to racial disparities in education AI systems. Now, just last month, we saw that the sentiment analysis tool in Google's new natural language API is labeling terms like black, gay, and Jew negatively. Meanwhile, terms like I'm straight or even white power were getting positive ratings. Last year, we learned that Amazon's same-day delivery service was bypassing zip codes that have large African-American populations. Now, this matters because for people who live in areas where they don't have ready access to a grocery store or a supermarket, places that are called food deserts, they can rely on same-day delivery to get fresh food. So it really matters if you're being cut off from the service. But take a close look at this map. It is eerily familiar, and because it looks just like these historical redlining maps of the US in the 1930s, when predominantly black neighborhoods were literally circled in red pen by the Federal Housing Administration, and people in those areas were being denied mortgages. And these maps remind us of the deep segregation that this caused. So the long histories of discrimination live on in our digital systems, often for very complex reasons, and they become buried into the logics of our machine learning infrastructures. Now, of course, the biggest of the bias blockbuster stories is this one by ProPublica, which looked at the use of compass scores in over 10,000 people in Florida and found racial bias across the results. Now, this study has been quite controversial, and there have been several important follow-on papers, including those by Choldakova, Kleinberg, Mullinaithan, and others. But these are just a few examples of some of the most well-known bias stories in the last couple of years. So put up your hand if you've kind of heard these. I'm expecting most of us. Yeah, excellent. That's what we want to see. So in my case, I've been researching issues to do with fairness and bias for the last 7 years, but have a look. It's really just in the last 18 months that it's gone from being a few of us working on this topic to it being a huge area of research interest. A shout out here to Moritz Hart, who made this fantastic chart. And of course, Moritz and Solon Barocas hosted a fantastic tutorial on fairness and machine learning yesterday, and I know a lot of you were there. And this surge of interest in bias questions is totally justified, because machine learning systems are starting to impact millions of people every day. So bias matters. But keep in mind that the common examples that I'm just sharing out with you today are just the tip of the iceberg. There are countless back-end systems below the surface, often applying off-the-shelf machine learning as a service systems that can propagate bias in ways that don't have a customer front end. And these ones are much, much harder to see. And the scale of this problem is now being acknowledged by leaders in the industry. In just the last 2 months, John Giandrea at Google, to Satya Nadella at Microsoft, to Mustafa Suleyman, who's one of the co-founders of DeepMind, have all called this a core problem for the field. In Mustafa's words, because of the scale of these systems, we can be hitting 1 billion to 2 billion users per day. And that means the costs of getting it wrong are very, very high. So this interest in bias is growing because machine learning is now a huge business. So when major platforms or services are found to be producing problematic results, that can be expensive as well as disastrous for the people it affects. But just as we're beginning to realize the scale of the bias problem, we're already seeing stories like this. Basically, that science has cured biased AI. Well, this kind of reminds me of what was happening 5 years ago when people were saying, hey, data is neutral, and then we realized it was anything but. Well, now we're hearing data can be neutralized. And while I think it's really tempting to seek out a silver bullet solution to cure bias, it's not going to work. One of my favorite conferences in this area, the Fairness, Accountability, and Transparency in Machine Learning Conference, which has been going for this is going to be its 6th year, has a lot of papers to show just how hard this problem is from a technical perspective. And you should check those out. They're all online if you haven't read them already. But here's what I want to talk about today. When we consider bias purely as a technical problem, which, let's face it, is hard enough, we are already missing part of the picture. Bias in systems is commonly caused, as we know, by bias in training data. And we can only gather data about the world that we have, which has a long history of discrimination. So the default tendency of these systems will be to reflect our darkest biases. Now, structural bias is a social issue first and a technical issue second. And if we are unable to consider both the social and the technical halves of this problem and to see it as inherently socio-technical, then these problems of bias are going to continue to plague the machine learning field. So even though some articles would like to tell you that the problem has been fixed, we got to brace ourselves. It ain't fixed. So I think there really is no silver bullet to this problem. But there has been some extraordinarily important work on it done by this community. And there's a lot more that we can do, which I'm going to address today. But the problem of bias runs much deeper than is normally admitted publicly. So I think it's time that we start talking about why bias is such a hard challenge. Because if we seek out the quick fixes, it's not only going to miss the deeper problem, we could actually make things worse. And I think that matters for the people who are going to be subject to skewed decisions, but it might also matter to the machine learning field itself. Because if our systems keep producing biased results, if people are unfairly kept in jail, or they can't get insurance, or they receive incorrect medical treatment, then people will no longer trust these tools or want to fund this type of work. So, as a twist on Game of Thrones, that could mean a new AI winter is coming. Something we don't want. So, there are a lot of reasons to care about this issue and get it right. So my talk today is going to address 5 themes. The first is, what do we mean when we say bias? Then I'm going to talk about 2 concepts that I'm going to explain in a moment. The first is harms of allocation, which are the types of harms that basically most fairness and machine learning research is focused on right now. The second category is harms of representation, which is where we urgently need more work. But then I'm going to talk about the big picture, the politics of classification itself, and what happens when we classify. And I'm going to end with some suggestions for what can be done to tackle these harder problems. So first of all, what do we mean when we say this word bias? Well, the big problem here is that bias has overlapping and sometimes contradictory meanings. And this is adding a lot of unnecessary confusion to some critically important discussions. Even the history of the word itself has different mathematical and social meanings. If we go back to the 14th century, the word bias first emerges in geometry to refer to an oblique or a diagonal line. By the 16th century, it had acquired something like its common meaning today of undue prejudice. But by the 1900s, bias had a technical meaning in statistics, where it refers to systematic differences between a sample and a population, and as we know, we start to see selection bias as a concept about errors in estimation when some members of a population are more likely to be sampled than others. And here's a picture that we all know and love well in the machine learning community. Of course, on the left, we have the classic visual representation of bias through underfitting, where a supervised model fails to capture the underlying trends in data. That's a situation where you have low variance but high bias. Contrast that with overfitting, situations of high variance and low bias, where models are extremely sensitive to small fluctuations, capturing noise in data along with signal. But this is really different, I think, to the popular and the legal definitions of this word bias. So, in law, as you would have heard in yesterday's excellent tutorial, bias means judgment based on preconceived notions or prejudices, as opposed to, say, the impartial evaluation of facts. Now, impartiality is one of those ideas that undergirds many of our legal processes, from juror selection to due process to the limitations placed on judges. Now, this sense of bias is much more difficult to fix with model validation techniques. And it can happen even when a model perfectly captures signal. For example, if it's reproducing biases because it was trained on data sets that reflected structural inequalities. So you can have an unbiased system in a machine learning sense, producing a biased result in a legal sense. So no wonder there are some real barriers to collaborating across disciplines on this topic. We're all speaking different languages. But it is precisely this ability to move outside of our disciplinary boundaries that we're most going to need if we're going to crack this problem. And let me give you some examples why. So where does bias in machine learning come from? Well, obviously one of the most common ways is from the data it was trained on. Now, training data can be incomplete, biased, or otherwise skewed. It can draw on non-representative samples that are poorly defined before use. And sometimes the problems with the training data set just aren't obvious because it was constructed in a non-transparent way, for example. Additionally, given that sometimes we have humans labeling the data and sometimes we don't, there are other ways that human biases and cultural assumptions can creep in, ending up in either exclusion or overrepresentation of subpopulations. Let's take Stop and Frisk, for example. This was a program that was run by the NYPD where 4.4 million people were stopped on suspicion between 2004 and 2012. Now, 83% of people who were stopped and frisked were black or Hispanic. So, you got an ML system that was using this data to refine its training model. One interpretation is that black and Hispanic people are just much more likely to be potential criminals. But if you bring in experts, from different disciplines, say like a constitutional law professor or a historian, they're going to tell you a different story and point to decades of systemic racial discrimination in policing. Now, that's actually what happened when stop and frisk was tried in the courts. It was actually found to be illegal as a form of racial profiling. So the social sciences and the humanities have decades of research on bias on social systems that I think have a lot to offer this current debate about bias in machine learning. So let's use this common meaning for a bit, that bias is a skew that produces a type of harm. So what types of harm should we, as a community looking at this problem, take into account? So I want to share with you some insights from a forthcoming paper by my colleagues Solon Barocas, Alan Shapiro, and Hannah Wallach. Over the last year, we've been studying all of the existing literature on bias in machine learning and how ML researchers are basically conceptualizing this problem. And what we've found is that the majority of the literature currently understands bias as producing harms of allocation. And let me tell you a little bit about what I mean there. An allocative harm is when a system allocates or withholds certain groups an opportunity or a resource. Now, this is primarily an economically oriented view, and it's centered on harms like who gets a mortgage, who gets a loan, who gets insurance. And an example here would be if, say, a mortgage support application just continually denied mortgages to women or to people under the age of 30. But this picture gets a lot more complicated when you look at systems that represent society but don't allocate resources. These are representational harms, and they occur when systems reinforce the subordination of some groups along the lines of identity, so that's race, class, gender, etc. This sort of harm can take place regardless of whether resources are being withheld to members of a protected class. Classic example there, of course, is Google Gorilla, where we saw that Google Photos was labeling an African-American woman a gorilla. Straight up representational harm. Let me give you another example. Many of you know LaTanya Sweeney's classic early study on discrimination in Google ad delivery systems back in 2013. She uncovered a pattern by which names that are associated with African Americans were yielding ads for criminal background checks. Now, in this paper, Sweeney argues that employers who are doing searches on job applicants will see these results, which may then lead to race-based discrimination in hiring. But there's a different way that you can look at this potential harm. Rather than moving downstream to the effects on opportunity and allocation, we can actually move upstream because representation is the first step in the chain. So our paper suggests that the perpetuation of stereotypes of black criminality is problematic even if it is outside of a hiring context. It's producing a harm of how black people are represented and understood socially. So instead of just thinking about machine learning contributing to decision-making in, say, hiring or criminal justice, we also need to think about the role of machine learning in harmful representations of human identity. So you can kind of see why allocation has tended to receive all the attention so far, because allocation is immediate. It's a time-bound moment of decision-making, whereas representation is a much more long-term process that affects attitudes and beliefs. Allocation is much more readily quantifiable, whereas representation might be more difficult to formalize. Put differently, allocation raises questions of fairness and justice in discrete and specific transactions, whereas representation is about this more diffuse depiction of humans and society generally. So one is transactional, the other is cultural. So representation bias issues have been neglected by computer science, mainly, I think, because it's just harder to formalize and track. But it is still incredibly significant, and it's at the root of all of the other forms of allocative harm. So what types of representational harms are there? So in this paper, we look at 5 different types, and I'm just going to quickly address a few. Stereotyping is probably the most well-considered so far. The classic Bullock-Bussey paper from 2016 on word embeddings was one of the first to really look at these gender stereotypical associations and the distance between gendered pronouns and specific occupations. Of course, the Princeton group, Kalaskan, Bryson, and Narayanan, found similar problems in their science paper this year. You probably all know this case of Google Translate, which is also producing stereotypical translations, even from gender-neutral languages like Turkish. So if you see here, you type in, he is a nurse, she is a doctor, you translate it into Turkish, you translate it back, and it actually swaps the genders of the pronouns. This is because some of these issues deep in our natural language models are actually just going to keep giving us these returns. And it's a problem that I know a lot of people in this room are really working hard on. The next area are harms of recognition. These occur when a group is erased or made invisible by a system. Now, in a narrow sense, the problem of recognition in machine learning is purely a technical one. Does a system recognize a face in an image or in a video? But there are some bigger implications here. It's also the failure to recognize somebody's humanity. Recognition in this broader sense, then, is basically about respect, dignity, and personhood. And there is a broader harm here than just whether or not a system works for you. And here I want to give a shout out to the work of Joy Buolamwini, who is a PhD student at MIT, who's been studying the way that facial recognition software cannot process darker skin tones. She actually ended up having to wear a white mask on her face for the vision system that she was studying to work for her. And she's got a poster here today at NIPS that you should go and check out. There are also similar errors. In work with Mike Anany, we've been looking at how Nikon's camera software mischaracterized Asian faces as blinking, and Hewlett-Packard's algorithms had difficulty basically recognizing anybody who was a darker shade of, like, completely pale. The third area is denigration harms. Now, this is just pretty straightforward when people use culturally disparaging terms. We had a really big one this year, of course, in autocomplete, where a huge media cycle got kicked off when people realized that if you typed in Jews should into a search query, the first thing you got back was Jews should be wiped out. Again, the case of Google Photos and the gorilla epithet is a pure case of denigration. What made it offensive here wasn't just that it got it wrong or it failed to work, but that it applied a label that has a long history of being used purposefully to demean people. So understanding problems of this kind requires understanding culture and history, something that's very difficult for a deep learning system to deduce. And it would really have required somebody in the room to say that this label could be offensive. Finally, there's this problem of underrepresentation. Now, I don't know how many of you have tried doing an image search on CEO lately, but you're going to get a lot of white dudes in suits. I'm sorry, it's just what you're going to get. And of course, there's a really important University of Washington paper that looks at how this happens in a lot of professions. Physicist, also, a lot of dudes. But when we looked at this, actually, about 6 months ago for the first time, we were really curious who the first female CEO would be. Can you kind of guess who it would be? She's right down the bottom on the end. It's CEO Barbie. Yeah, seriously. First female CEO, Barbie. Not a great look. So, we ended up creating this table to map out some of the most well-known bias cases against different types of representational harms. As you can see, something like the Google Gorilla case is a pure case of denigration, but if we look at the word embeddings implicit bias paper by Bullock-Barsi, etc., it hits across all categories, from stereotyping to denigration to underrepresentation. And I think doing something like this is actually incredibly helpful because we get a more fine-grained, sort of granular analysis of what the harms are, so we can actually start to remediate them better. So how do we tend to address these issues technically? Well, in this paper, we've basically looked at all of the technical responses so far to allocative harms. And these are the full set, but I'll just speak to a couple. Scrubbing to neutral is basically one of the most sort of common responses that I've seen, where people say, we'll just remove the biased data, or we'll break the problematic association in, say, a word embedding model. But who gets to decide which terms should be removed, and why those ones in particular? And an even bigger question here is, whose idea of neutrality is at work? Do we assume that neutral is what we have in the world today? And if so, how do we account for, in some cases, hundreds of years of discrimination against particular subpopulations? This problem also comes up when we try to technically address the underrepresentation issue. So should you go to demographics and basically make your representations adhere to current distributions in society? Well, I mean, let's take the CEO image search as an example, right? So we know that less than 8% of CEOs in the world right now are women. So does that mean that your image search results should show 8% or less of women? Or do we already sort of think about the fact that there are studies that show that have been discrimination against women getting into the C-suite? So do we then try to change the image search results to have distributions that we think would be fair or as we would like them to be? This is actually a really hard decision. This is not a straightforward question, and it actually has a lot of political implications, as you know. So while these kinds of technical responses are incredibly important, and we need more of them, they won't get us all of the way to addressing representational harms to group identity that we've outlined in this paper. Representational harms often exceed the scope of individual technical interventions. We're basically talking here about how we represent human culture, and that requires a different theoretical toolkit. In short, only developing theoretical fixes that come from the technical world for allocative harms is necessary, but it's not sufficient. So we need to consider the bigger issue underlying fairness and bias. So far, I've shown you how we consider bias harms from both an allocative and a representational perspective. Allocation focuses on resources and economic benefits, while representation focuses on identity categories like race and gender as they already exist today and how they're being reinforced or denigrated. But now we can take a step back and ask, where do these identity categories come from? Because the most common approach to think about bias today is to think of it as a kind of pathology, an error that turns up that we can fix. But what if bias is actually a deeper and more consistent issue with classification? In other words, what if bias is always going to be a problem? The fact that bias issues keep creeping into our systems and manifesting in new ways suggests that we need to step back and understand classification as not simply a technical issue, but a social issue, one that has real consequences for people who are being classified. So in order to show you why I think this is the case, I'm going to take you on a high-speed tour of the very weird history of classification, which I think has got some really applicable lessons for the machine learning community. But there's two themes, I want you to keep in mind. The first is that classification is always a product of its time. And the second is that we are currently in the biggest experiment of classification in human history. So to understand classification, we're going to go back. We're going to go way back to one of the most founding figures in this entire area, who is, of course, Aristotle, the guy in the blue robe who is staring adoringly at his teacher, Plato, in the pink robe. So Aristotle's work on natural classification was revolutionary at the time, but has now become basically scientific common sense. He went out into the field, he made observations of living things, and then he drew general conclusions. Yeah, this is basically the inductive method of empiricism. But even from really early on, we can see how classifications also reflect the social order of the time. Have a look at this image. I love this one. It's from about 300 years after Aristotle. It's from a really influential zoological illuminated manuscript. And it shows how religious themes were being built right into these classifications of the natural world. So you've got animals marching 2 by 2, and you have a Christ figure that's sort of ushering them along. So we're starting to see religious ideas mix freely with zoological classification. So the history of classification shows us time and time again that every attempt to classify will always reflect the social, cultural, religious, and political issues of the time. Now, during the Enlightenment, philosophers were very emboldened by the success of the natural sciences. They wanted to create a taxonomy of the entire universe. This is actually one of my favorites. It was created by the 17th century scientist John Wilkins. He's one of the founding members of the Royal Society. And he publishes this formative book that classifies the entire universe into 40 categories. Kind of handy, right? It's nice to have just 40, makes everything pretty straightforward. And if essentially Aristotle was taking an empirical approach to classification, Wilkins shows the later popularity of a linguistic approach, where human language is ordering all of our experience. And another 17th century thinker, Thomas Urquhart, proposed an artificial language called the Logopandensian. And this classified the whole world into 11 genders. So you had men and women, but you also had gods and goddesses and beasts and inanimate objects, etc., etc. So while these classificatory schema can seem kind of arbitrary and funny today, the takeaway here is that the work of classification is always a reflection of culture, and therefore it's always going to be slightly arbitrary and of its time. And modern machine learning is making decisions that fundamentally divide the world into parts, and the choices that we make about where those divisions go are going to have consequences. So let's talk about gender for a minute. Urquhart says there were 11 genders, that's back in 1653. 2017, Facebook says there are 56 genders. Okay, that's a very precise number. And of course, 4 years ago, Facebook said there were only 2, men and women. So obviously something very interesting has happened in the last 4 years. And while you might say this is an improvement, it's still pretty arbitrary. You can imagine that something like this is basically the product of a design meeting where a bunch of people are in a room with a whiteboard and they're trying to brainstorm every single gender category they can possibly think of. But of course, they could have also just gone with a free text field for self-identification or just not had gender at all. Each one of these design decisions, in effect, has consequences and powerful social implications. Let's consider the world of machine vision for a second and the labeled faces in the wild training set. It's incredibly important. It's been cited over 2,000 times. And it doesn't claim to make any sort of grand classification of all of the faces in the world, but it does have some notable biases, as Joy has pointed out. It's 77.5% men, 83.5% white. So those are the people for whom a system trained on this are going to work best for. And who do you think the most represented face is in labeled faces in the wild? Have a guess. Anyone know this one? Put up your hand if you've kind of heard this story before. Anybody? Oh, this is great. It is George W. Bush. Yeah, he is the most represented face. He's in there 530 times out of 13,000. And this kind of makes sense when you remember that labeled faces in the wild is based on Faces in the Wild, which came from photos of Yahoo News from around 2002 to 2004, with the idea that news photographs, unlike those taken under lab conditions, are more true to life. So no wonder that W is everywhere, because of course, presidents get a disproportionate amount of news attention, as we've kind of discovered to our peril this year. And this is ultimately a great reminder to me of a couple of things. The first is that data sets reflect the culture, but also the hierarchy of the world that they were made in. Who is powerful is going to appear a lot more frequently than who is not. So we have to ask, what happens when you choose news photography? And does that change your interpretation of faces? What kinds of people are always in the news, and who's not there? Secondly, I think this really reminds us that our current data sets always stand on the shoulders of older classifications. So ImageNet draws on the taxonomy of words that come from WordNet, and WordNet inherits from many sources, including the Brown corpus from the 1950s. So while we might look at a picture like this, which comes from Diderot and d'Alembert's encyclopedia from 1751, and think, well, this is pretty old-fashioned. I mean, you can't really categorize the world into so few categories. I think machine learning is also developing its own, sometimes arbitrary, sometimes strange, culturally specific classifications. So what would it look like, just imagine, if we tried to create an encyclopedia of machine learning like Diderot's image here? Well, we thought we'd give it a shot just for NIPS, so here you go. It looks a little something like this. You can see here how early various contemporary data sources are building on earlier corpora. So let me zoom in for a bit. You can see here current data sets like CIFAR, ImageNet, MS-COCO, and Kinetics, and you can see what they draw on and what came before them. You can also see how training data sets are already conducting the largest classificatory experiment the world has seen. It's everything from human faces, human poses, every human action, to millions of objects and places and natural phenomena. But some of these classifications are going to change, like Facebook's gender categories, but some of them are going to hang around because classifications can be sticky, and sometimes they stick around a lot longer than we intend them to, even when they're harmful. Let me give you an example. This is the cover of the Diagnostic and Statistical Manual of Mental Disorders, first published back in 1952. This listed homosexuality as a serious mental disorder. Now, that took over 30 years before that was finally dropped. And if that sounds like a really long time to you, I was kind of amazed to find out that the Dewey Decimal System, you know, what we use to categorize books in libraries, listed homosexuality in 1932 as a mental derangement. And it has remained there until 2 years ago, 2015. Yeah. So people who are classified as gay were then being further classified as having a mental disorder and being a social problem. And this had devastating consequences for people who were identified this way, and it took an enormous amount of protest and advocacy to address this kind of classificatory harm. And frankly, it continues to reverberate even when the worst labels are removed. But now history is repeating itself. Yep, you know where this one comes from. This is the Wang and Kaczynski paper that is on deep neural networks detecting sexual orientation from facial images, and it caused a huge controversy this year. Now, they used the VGG face from the Oxford Vision Lab, and they trained it on facial images of white men and women from a dating website, unnamed, and Facebook. And their classifier achieved 81% accuracy in identifying gay men and 71% accuracy in identifying gay women. Now, many members of the scientific community have expressed concerns both about the representativeness of the researchers' sample and whether these images are just reflecting cultural markers of sexuality rather than purely physical features that they didn't control for. But I actually don't want to talk about these methodological problems right now. I think we need to think more about the ethics of classification here, particularly when we think about the fact that homosexuality is still criminalized in 78 countries, some of which apply the death penalty. What we see here is how easily machine learning can be deployed in contentious forms of categorization that could result in criminal prosecution, jailing of people, or worse. So our responsibility for the systems that we create, particularly in terms of these classifications, has never been higher. So I've shown you how classification systems are often sites of political and social struggle. And as Bowker and Starr showed in their basically now canonical book about classification called Sorting Things Out, political agendas are sometimes presented as purely technical and then hidden away from the public, and they gradually become taken for granted. They write about a really important study, actually, of apartheid South Africa to show how classifications can be used for authoritarian political control. This image comes from something called the Book of Life, and it was used in South Africa during the height of apartheid in the 1970s. It classified people into one of 4 categories: colored, Indian, white, or black. And it was then built into a technical passbook system by IBM at the time. Now, depending on what category you were classified in, it would determine where you could live, what job you could have, and who you could marry. And you were basically classified according to this really ambiguous criteria of your appearance and general reputation. So you can imagine how messy that got. This person here is Vic Wilkinson. He was a jazz musician, and he got racially recategorized 5 times by the South African government, each time producing huge disruptions in, what jobs he could do and his freedom of movement. Now, fast forward to 2016, when Wu and Zhang published this paper that claimed it could predict the likelihood that a person is a convicted criminal based on nothing more than a photo of somebody's face. Now, as we know, they did this by training their system on around 2,000 Chinese government-issued IDs, and they then concluded that they'd created the first ever free-of-bias criminality detector. Right, well, I tend to think we should be pretty skeptical of these claims. Basically, it's saying that this is a neutral system superior to human judgment, which is basically the big red warning sign given the human biases that affect who is arrested and who is charged with crimes. So this is not free of bias. This is just bias encoded. And of course, this type of face-based prediction has all happened before. Physiognomy and phrenology were considered sciences back in the 19th century, but they had a very nasty pattern of being used effectively to justify the unjustifiable, including slavery in the US and being used by race scientists in Germany in the 1930s. And if all of this sounds like the distant past, know that there are already startups making money based on these questions. Oh, we just lost the slides, but that's okay. I'm sure they'll come back. Making money on these sorts of issues by saying that they can predict who is a terrorist as well as who is going to be something like a brand manager. So I think these are the sorts of questions that should really begin to concern us as a community, and I'm going to see if I can bring us back with some pretty images to conclude, but maybe that's a bit optimistic. All right, it was optimistic. We'll do it without. What I want to do now is end on 3 things that I think we can do as a community to start to contend with these problems. And I'm going to do it straight off the top of my head. So the first one that I think is really important here is that we need to start working on fairness forensics. And what I mean by this is that there are a lot of things that we can start to do to really test our systems. This includes everything from building pre-release trials where you can see how a system is working across different populations. So that means you actually know if it's affecting black populations differently to white populations. Oh, not my slides, but that's okay. We can also start thinking about questions like, how do we track the life cycle of a training data set to actually know who built it and what the demographic skews might be in that set? I also think it's time for us, number 2, to really start taking interdisciplinarity seriously. That means working with people who are not in our fields, but might have deep expertise across other areas. Now, personally, one of the things that I did, along with Hannah Wallach and others, was to build the FATE group at Microsoft Research. That stands for Fairness, Accountability, Transparency, and Ethics. And this is something that you can do too. If you are working at a company that is basically building high-stakes decision-making systems, then you can actually think about building an interdisciplinary group that starts to test how it's working. I think this is incredibly important. The second thing that I've been doing to work towards this goal is I've just launched a new research institute called the AI Now Institute, along with my co-founder, Meredith Whitaker. The reason we did this is because we think it's incredibly important that we start to have spaces where disciplines can actually work. It's cool, we're going to do it without slides, we're going to freeform it. Where disciplines can actually start working together on these problems. So for the AI Now Institute, it includes computer science, engineering, social science, law, and business. So in that sense, I think we can start to build these spaces for collaboration on these questions. Finally, my third recommendation is that I think we need to think harder about the ethics of classification. Right now, you might have heard that the Trump administration is asking the machine learning community to help build tools for extreme vetting at the border. Now, I and around 50 other academics, some of whom are in this room, have signed a letter saying that we think this is actually a deeply concerning system. And frankly, I think it's concerning not just because of the potential technical problems, but also because I think it raises huge ethical questions. So the question here for the industry is, are there some things that we just shouldn't build? And if so, how do we start to have that conversation? And also, I want to talk about us as individuals. How do we start to make decisions about what we should do and what we shouldn't do? Because this community in the room right now has an enormous amount of power, and your decisions are going to make a difference. So I'd like to remind you of a particular engineer that is a hero of mine called René Camille, who back in the 1940s sabotaged the Hollerith machines that were being used to classify Jews and other ethnic minorities in Germany. And basically by erasing the 11th column on the Hollerith machine, he made an individual decision that saved thousands of lives. So ultimately, when it comes to the question of fairness in machine learning, I think we have to ask ourselves the big question. Who is going to benefit from the system we're building, and who might be harmed? Because if we're really interested in the question of fairness, that's the most important question that we can ask. Thank you very much. Thank you. I think we have time for a couple of questions, if Hannah is going to permit us. Yeah, got time for one or two. Fantastic. Thank you very much. Just there are a couple of mics up here. If people have a question, feel free to dash to one of these. Yeah, we just have one over here. Hi. Yeah, I can hear. I love this question. This is a really important design question. I'm going to repeat it for people who couldn't hear that. The question is, who gets to decide how we tune our systems? Because traditionally this has been done by computer scientists, sometimes thinking about a specific user group that they're trying to sell a product to. How do we start to open up that field of questions to start asking different populations? Fair enough? Got your question? Yep. That's it. So the issue here is that right now we interview the customer to find out what they want. And I think that's exactly right. This is the history of how we've worked as a field for decades. I think we now have a slightly different set of questions to ask. And I'd put it this way. If you're building a high-stakes decision-making system that's going to affect some populations more than others, so here criminal justice is a classic case in point, you need to start thinking about different questions than just the customer. You need to say, okay, this is a complex social system, so who's going to know the best about it? Let me give you an example. Right now, we have predictive risk scores, as you know, that are being used in criminal justice contexts. And one of the big areas that it looks at is this idea of failure to appear. So a defendant will get a score based on how likely it is that they're not going to turn up to their court date. That kind of makes sense, right? But if the judge looks at that number and says, okay, this person is high risk, then basically they are detained. They are jailed. They actually don't get out on bail. So this is a big issue, failure to appear. Now, if we start to look at research outside of, say, just how do we tune the predictions, you will also look at research from sociology and anthropology that shows you that the thing that really affects failure to appear for court dates is things like, did that person have transport? Could they get there? Did they have childcare if they're the primary carer of their family? So the things like trying to get people transport, trying to set up childcare for court dates, might actually have a much bigger difference than just giving people a score of high risk and not letting them go. So I guess this is a much more complex set of questions than computer science is normally having to deal with, and it's something that I've called a social systems analysis, and I've written about this in Nature with Ryan Kalo last year, and I'm happy to share that with you if it would be useful. But I think this is precisely the moment where computer science is having to ask much bigger questions because it's being asked to do much bigger things. But that's a great question. Thank you.
Thank you.
I have a question here. Yes, please. Mm-hmm. Yep. Wow, this is a really big question, and let me repeat it for you. So the question is, if we take, for example, this community being asked to do things that could be quite socially problematic, how do we compare that to, say, what was happening with the nuclear scientists who, actually formed groups and said, no, some of these things are actually too dangerous for us to do. And because there was really only a small group of people who were skilled enough to build those large-scale systems, if they walked away, it wasn't going to get done. But that's not the case in machine learning. If this community says, hey, we're not going to work on these tools, somebody else is just going to step up and do it really badly. So how do we deal with that question that if the community of people who have the most training say something is really suspect and problematic or ethically concerning, what happens if somebody else just goes and does it really badly? So I actually think this is a really hard question, particularly now that we're starting to see a lot of these sorts of tools basically be sort of shared out, so really anyone can start to play with things like TensorFlow, etc. So I actually think still this community has an enormous voice to say things like, okay, we don't think this system is okay. Now that doesn't mean that we're going to stop people from doing it, and particularly this gets really interesting when you think about the geopolitics of how systems get built. Even if one country decides that something is not acceptable, what happens if that's being built somewhere else? I don't have an easy answer for you for this question, but I do think that particularly the senior people in this community, in this room, have a huge sway to be able to say, hey, these are the kinds of things that we can start to make progress on. So to some degree, I think it's up to us, but I know that that's going to be a really hard path, and some of these questions are just going to get more complex, not less. That's Hannah giving me the signal. Thank you so much for your time.